All right, so we are talking today about the Bronsted-Lowry theory of acids and bases. In Chem 20, you would have learned about other people's ideas about acids and bases. These are the guys who won the prize to be our discussion this year. Last year, this is the idea that you would have focused on mostly in the unit on acids and bases. First, you would have looked at Arrhenius's dissociation theory. This is the wrong one. This is where he said originally, hey, I put an acid in water and it dissociates, becomes hydrogen and some other ion, and that's it. Then he came up with his modified theory that wasn't, oh, no, acids don't dissociate in water, they react with water to produce hydronium. Now, we know that this was the better version, so that is the one that I want to actually write down. I don't want you to write down the one that was wrong or the one that came first. So he said acids react with water to produce hydronium. Now this shouldn't be news because we just did that in the last several lessons. We showed how when you react an acid with water, you produce hydronium. He also said that bases either dissociate if there's hydroxide or react with water to produce hydroxide. Now, we used both of those ideas over the last 3 lessons so that we could write the reaction of an acid or a base when we put it in water. So none of this is like a new shocking turn of events. This is all stuff that we knew from before. Now, this is still true, this is still good, but we're just going to add on what Bronsted and Lowry said. Instead of talking about what the acid reacts with or what the acid is producing, we focused on whether the acid or the base is accepting or donating something in the reaction. So, if we consider the reaction of hydrogen chloride makes hydrochloric acid, which is a typical acid that we use in lots of our labs. But when hydrogen chloride reacts with water, a proton, in other words, hydrogen ion, is transferred. That is the basic premise of every acid-base reaction. A proton, a hydrogen ion, is being transferred. It is being transferred from the HCl to the water. So if we look, HCl is a proton donor, and water is a proton acceptor. And this is what you have to be able to do. You have to identify which substance donates the proton and which one accepts them. Now, I would always talk about my reactants as one set of substances. Generally, I only have reactants at the beginning of a reaction, and I don't have products until the reaction starts happening. So I wouldn't say that HCl donates a proton to something that's on the right, because that's not what it's reacting with. It's reacting with water. Now, the pH of the water drops, decreases, gets lower, whatever you want to say, as more and more HCl is dissolved. Now, if you look at what's happening, well, that makes sense. The more HCl I put in, the more hydronium I'm going to make. More hydronium means lower pH. Now, in a similar example, we could take ammonia. So ammonia we saw was a base. In this case, there's still going to be a proton transferred, but this time it's going to be transferred from the water to the ammonia. Water is the proton donor. Ammonia is the proton acceptor. Now, how did I know, especially in this example, because ammonia has hydrogen, it could have donated one. How did I know that it wasn't going to donate but accept? In a lot of cases, it'll be easy because only one of them has hydrogen. But in many other cases, like this one, both things will have hydrogen. So you are going to use your bestie, the data booklet, where so many answers can be found, and you're going to look and say, oh yeah, there's that table that tells me whether things are acids or bases. Oh look, ammonia is on the base side, so I know it's going to act like a base, and it's going to accept a proton instead of donate one. Now in this scenario, the pH of the water rises, increases, gets larger as more and more ammonia is reacted. Why? Well, look at what I'm making. I'm making more and more hydroxide every time I add more ammonia to the reaction. If you look at the reaction arrow, notice that this one is an equilibrium. The first one was a quantitative reaction. That's because ammonia is a weak base, not a strong one. Now, in the last two examples, we had something reacting with water, something reacting with water. But we don't actually have to add water as a reactant. It would be possible to have hydronium reacting directly. So in this scenario, one of these hydrogen ions will be transferred. Hydronium will be the donor, and ammonia will be the acceptor. Now, typically, we would write just the formula for the acid, unless it's a strong acid. So anytime you have a strong acid in the question, instead of writing its formula, you can just directly write H3O+. And the reason is, like we discussed in Lesson 7, 100% of a strong acid ionizes and becomes hydronium. So it's all going to be hydronium. I can just write hydronium in its place. Now, if I'm adding hydronium or a strong acid to ammonia, the pH of the ammonia drops as more and more hydronium reacts with it. Now, why would that be true? Well, the ammonia had a high pH, and now I'm adding something that had a low pH. Now, if we could summarize what went on in those three examples, where I'm saying Bl, I mean Bronsted-Lowry, which was the title of the lesson. A Bronsted-Lowry acid is a proton donor in a chemical reaction, and a base is a proton acceptor. Now, just because something was a Bronsted-Lowry acid or a Bronsted-Lowry base in one reaction doesn't mean in another reaction that's still what they will be. Classifying things as Bronsted-Lowry acids or bases is specific to a particular reaction. So for example, in the reaction where I had HCl and water, in that case, water was the Bronsted-Lowry base. But in the reaction where I had ammonia and water, water was the Bronsted-Lowry acid. Now, not every substance can do that, be an acid or a base. There's only a few that can. When something could be an acid or a base, we call them amphiprotic, or sometimes you might see amphoteric. Now, An amphiprotic substance, like I said, could be water. Water is probably the most frequent substance that you'll see, but I don't think the diploma will ever ask you, is water amphiprotic? Because everyone knows that it is. It's the way you explain what amphiprotic means. So when you're looking for something that's amphiprotic in general, you are looking for a negative ion with hydrogen. There are lots of things that would fit into that category, and so I'm just going to show you a few examples of what that might look like. For example, HCO3 negative. Because it has a hydrogen right here, it could be a donor. It could give that hydrogen to something else. To be a proton donor, you actually have to have a proton. Because it has a negative charge over here, it can be a proton acceptor. Things that have a negative charge could easily and readily accept something with a positive charge. Now, there are lots of things that would fall into this category, most of which won't be in your data booklet already. If we're going to ask you about something that's amphiprotic, the diploma writers love to pick some random, ridiculous ion that you've never seen before in your life and ask you about it. But if you can identify those two pieces, a hydrogen that it could donate and a negative charge, then chances are it's amphiprotic. Now, I just want to caution everybody with an example like this one. That's a negative ion, and it has hydrogen, but it doesn't have hydrogen that it can donate. For the hydrogen to be donatable, it should either be at the beginning, like in the bicarbonate ion, or you should see it at the end of the organic acid formula. In this case, you don't see it there. These hydrogens here that are attached to carbon, these are unlikely to be donated as an acid. So that would be something that you would look for as a trick or something that's trying to fool you. Those hydrogens are not going to be donated. Now, does anyone want to ask any questions about donating or accepting? Yeah. No, hydrogen ions don't have neutrons. If you remember, if you look at the molar mass of hydrogen, some of them might, but the vast majority of hydrogen atoms are just one proton and one electron, no neutron. Now, if we consider the fact that something is donating and something is accepting the proton, and then we think about equilibrium. At equilibrium, which is the focus of our unit, the forward and reverse reaction are both happening at the same rate. That means that there is a Bronsted-Lowry acid and base on both sides of the reaction. So what would be typical is to ask you to identify something called a conjugate acid and base pair. If we look at this example of acetic acid here, I would be able to identify that what happened is that acetic acid donated a proton to water. I would call this the Bronsted-Lowry acid, and this the Bronsted-Lowry base. That's if I was looking at the reaction as if it was proceeding from left to right. But it's equilibrium, so we know the reaction could be happening from right to left as well. So if I look at these two substances that are on the right, and I ask myself, if I read the reaction as if it was reversing, what's happening? Well, that's what would happen if I were to reverse the reaction. In that case, this is the Bronsted-Lowry acid, and this is the Bronsted-Lowry base. Now, like it says, there is a Bronsted-Lowry acid and base on either side of the reaction. If you look, though, the Bronsted-Lowry acid here and this Bronsted-Lowry acid really have nothing to do one with the other. Yeah, they're both acids, but they don't have the same formula or anything. We are interested in something called a conjugate acid-base pair. It is a pair of chemicals that differ by only one proton. So, going back to my example, a conjugate acid-base pair would be something like this. Acetic acid and the acetate ion, they are the same except for one proton. That is the only thing that really should guide your decision on what a conjugate pair is. Typically, a diploma-style question would give you some random reaction and say, what's a conjugate acid-base pair? And it will give you a bunch of ridiculous choices that are not different by one proton. That's what you should look for and eliminate anything that has more differences than that. These two are also a conjugate acid-base pair. Why? They are the same except for one proton. One has one more proton than the other does. Now, if they were not part of the same reaction, they couldn't be conjugate. They have to be in the same reaction. So same reaction and different by one hydrogen, one proton. Now, if we consider the two things that are in a conjugate acid-base pair, if the acid is stronger, then the base will be weaker. And if you look at your data booklet, that makes tons of sense. If the acid is stronger, it's higher on the left. If it's higher on the left, it means the base is higher up, and we know that bases get weaker as you go up. So if the acid is a strong one, the conjugate base that goes with it will be a weak one. That's what we're showing you in the data table, a bunch of acids and their conjugate base. If you get to the question about conjugate pairs and you forget what the word conjugate means, I hope that at some point you look in your data booklet and you say, oh yeah, it's telling me what a conjugate pair is right here. The other thing that would be true is that if Ka increases, Kb decreases. Right? Ka is basically telling us how strong the acid is. So if it's bigger, Kb will be smaller. The other reason that makes sense is that we know Ka and Kb are related by Kw, and so if one of them gets bigger, the other one has to be smaller, otherwise they won't be equal to Kw when you multiply them together. Now, does anyone want to ask anything there about conjugate pairs? So, just as an example, if you consider methanoic acid, methanoic acid has a Ka that is stronger than hypochlorous acid. Remember that when you have negative exponents, you really have to consider which one is bigger. Sometimes people might say, well, 4 is bigger than 1.8 and 8 is bigger than 4. Isn't that a bigger number? No, it is not. The more negative the exponent, the smaller the number. If we compare their conjugate bases, though, and that's what these are, is conjugate bases, it's the opposite. Methanoic acid was the stronger acid, but the hypochlorite ion was the stronger base. Now, does anyone want to ask anything about the relationship between strength and the conjugate pair? Now, sometimes you will have an amphiprotic substance, something that could be an acid or could be a base. And you need to figure out what would its Ka be and what is its Kb value to determine whether or not it would act as an acid or a base. Now, we're going to look at HOOCCOO. So that is a negative ion that has hydrogen, which was like the perfect definition for something that's amphiprotic. If I look up its Ka value in the data booklet, so you would find that on, I'm just going to find the best line here. It's on page 8, so it's your hydrogen oxalate ion, and its Ka is 1.5 times 10 to the power of negative 4. And we're interested, would it be stronger as an acid or would it be stronger as a base? Well, what's its Kb value? You have to look at the line where it is actually the base. So some people might accidentally stay on the same line and try to calculate Kb. What you actually want to do is find the line several spaces higher where HOOCCOO negative, our oxalate ion, is on the base side. So to find Kb, I'm going to take that 5.6 times 10 to the power of negative 2. That's the Ka value on the line where hydrogen oxalate is a base. Okay? Now, does anyone have questions about where I'm getting these numbers from so far? So I know that to find Kb, I should do Kw divided by Ka. And so what I'm trying to show you is I need to make sure I use that second Ka value, the one that came from the line where hydrogen oxalate was actually a base. And I'm just going to check my number here because I can't read my own writing. All right. So if I take Kw and divide it by the Ka from the line where the thing was a base, I end up with 1.79, we probably round that, times 10 to the power of negative 13. Now, neither of these is my official answer, so I'm not super concerned with significant digits just yet. Ka is clearly way bigger than Kb. Now, I did a lot of work to figure that out. Does anyone know how I could have figured that out without calculating anything? Because I could have. Person who's not in my class but is sitting here anyway, do you know how to tell whether Ka or Kb was bigger? Oh, he doesn't. Look in the data booklet and look at their position. Do you remember when we did voltaic versus electrolytic cells? We were trying to decide, is the oxidizing agent higher than the reducing agent? Same idea here. Is the acid higher than the base? Yeah, then the acid's stronger than the base. Is the acid lower, or is the, sorry, what am I saying here? The base is high, which makes it weak, and the acid is fairly low down here. If I look just at the numbers, though, I could eyeball this. Negative 4 is the exponent for the hydrogen oxalate ion. Negative 2 is the exponent for the Ka up there, and I know that Kw is negative 14. Without even calculating it, I know that the relationship between this value and Kw is super, super, super small. So I could have figured this out without necessarily calculating it. In some cases, it'll be easy because the Ka will be higher on the list than the Kb, and you'll be able to just look at it in terms of position. Now that we know that Ka is higher, this is bigger, my conclusion is this is going to act as an acid, not as a base. Even though it could have acted as either, it's more likely that it's going to act as an acid. So when I write the reaction, with water, it's equilibrium because this is certainly not a strong base. I'm going to write it as though this is donating a proton to water. So because Ka was bigger, I decided it was going to make an acidic solution. That means in my reaction, I will have OOCCOO 2 negative plus H3O positive. Now, it's not often that you have to decide for an amphiprotic substance whether it's going to act as an acid or a base, but if you do, that's how you decide. Figure out whether it's Ka or it's Kb is bigger. Ka you get from the line where it's an acid. Kb you calculate from the line where it's a base. Now, does anyone want to ask any questions about that part so far? Everyone's good there? So now we got to figure out the pH of this solution. Now what do we have? We have a weak acid, same thing we did in lesson 7. So I need to figure out the concentration of hydronium so that I can figure out the pH. That's my goal. Now, earlier today, someone asked me, like, how come I have to do a calculation to find the concentration of hydronium? Don't they have the same coefficient? Well, yeah, my acid and my hydronium do, but remember, this is not a 100% reaction. So we use our Ka expression. Where we multiply our negative ion and the concentration of hydronium, and we divide it by the concentration of our acid, in this case, hydrogen oxalate. And we remember that even though we're looking for equilibrium concentrations, the concentration of the acid, the 0.150 moles per liter, will decrease by such a small amount that when I round it, it's going to be the same number. So 0.150 moles per liter here. We don't know the concentration of either product, but we do know that they should have the same value. So we'll represent them both by X. And we know the Ka because we looked it up before, 1.5 times 10 to the power of negative 4. Now, once we figure out X, remember that X, if you've forgotten, is telling us the concentration of hydronium. So in this scenario, when we simplify and we find X, we end up with 0.004743 moles per liter, which is the concentration of hydronium. To do that math, I multiplied these two numbers together. Then I took the square root of that so that I could get the value of X. Does anyone want to ask questions about the math that goes along with this or any step of that calculation? Okay. Once I have this value that I will not round because it's not my final answer, I can do negative log of the concentration of hydronium, and I can figure out that the pH is 2.324. Now, does anyone want to tell me why I left 3 decimal places in my answer? Yeah? First number doesn't count, so first number is not part of significant digits. Yeah. Sure. Oh, you're asking me like in terms of work. This is my suggestion for how to do work, but if you feel confident in what you're doing, I just need to see what you did to get the answer. And remember that if you're doing an exam question, you're picking A, B, C, or D, and so your method, like how you're going to solve it, is really your call. So I would always suggest writing down more is better than writing down less. In case you forget what you're doing, sometimes when you write down a bit more, you notice, oh, that seems wrong and I shouldn't be writing it. As long as I can see what you did as your calculation, though, I wouldn't take off a mark if you simplified a step earlier. I think that's what you're asking, yeah. Okay. Now that brings us to the end of this one.